here I've got that again, 21.37 and 3.02. Our second step then, we need to look up the other variables that we need. So I put the equations here. We have now x bar bar. We have r bar. We need to find A2. We need to find D4. And we need to find D3. And again, these constants are what allow us to construct control limits that reflect the 3 sigma variation of our process characteristics. So we go to our table, and what was n? N equals 5. There's our n equals 5. We needed A2, we need D3, and we need D4. So for n equals 5, we find that A2 is 0.577, D3 is 0, and D4 is 2.114. So now we have everything we need. X bar bar 21.37, R bar 3.02, A2, D3, and D4. So control limits. For the upper control limit of X bar, so upper control limit X bar, we need X bar bar, which is 21.37, plus A2, 0.577, times the range bar, 3.02. If you calculate that out, you get 23.11. The center line for X bar is going to be simply 21.37, and the lower control limit for X bar is going to be X bar bar minus A2 times range bar, which is equal to 19.36. So our upper and lower control limits. For the range, the upper control limit of the range is going to be D4 times R bar, which gives us then 2.114 times 3.02, which equals 6.38. The center line for the range, simply R bar, which is 3.02, and the lower control limit for the range equal to D3, R bar is equal to 0 times 3.02 equal to 0. So we're not completely finished, but we have used our first 24 samples to find the natural control limits for both the X bar and the range. So now we need to plot this. Okay, so here's our data again. Sorry, this is a busy slide. Here's the data that we used. Here we see our X bar chart and our R chart. Here we see the upper control limit of 23.11, the center line of 21.37, and the lower control limit of 19.63. And all these points here for X bar then, we can plot on our chart. And the same for the range. We have upper control limit of 6.38, center line of 3.02, and lower control limit of 0. And all the range values then are plotted here. So now what can you tell me, what do you notice here in these charts? Let me draw here the upper control limit for the X bar and the lower control limit for the X bar, upper control limit for the range, and the lower control limit for the range. So I think you can all see that one of the range values is not in control. So what does this mean? And what should we do? What do we do now? So the first thing is we learned that these control limits should contain 99.73 of the data. So we first need to find the assignable cause for the out of control sample, remove that data point, and recalculate the limits. Since X bar and R are statistically independent, we could, in this case, we could just remove that R value. But since it's known that the process was out of control, it's probably advisable to remove both X bar and R after eliminating the assignable cause. The new limits can then be calculated for future use using from the remaining data to save some time and money. And one note, while making these calculations, it's always good to start with the R chart, because you need the R bar in order to calculate the X bar. So probably you're already asking, we already started with 24 instead of 25. How many of the original samples can we throw out before we have too few samples to make our control chart calculations? And so the answer here is part practical and part statistical. I mean, the recommendation is that we should take at least 25 samples of size 4, but the sampling costs time and money. So maybe we can't delay. So in practice, as few as 15 samples are often used. And these limits can be updated when new samples are available. Or you can play it safe and you could take many more samples, say 30 samples at the beginning, with the expectation that a few of these will be out of control and need to get thrown out. But one thing to remember is that the constant A2 times R bar is used for estimating the 3 sigma limits is not very good when R bar is obtained from a small number of samples. So we have a trade-off here between N, the number in each sample, the number of samples, and our time and cost for generating the first control charts. So as conclusion for this, if you have a sample size of 4 or 5, then use no less than 15 samples to calculate the limits and recalculate as more samples become available. So let's go on back to our example. The one R value outside the upper limit, we remove that. And we assume in this case that we've found the reason and we've rectified it. The new R bar can be calculated. Instead of 3.02, it's 2.85. Of course, it's less because that was so high, from the remaining 3 observations. And this gives us new limits now of 23.02, 19.72 for our X bar, 6.02, and 0 for our R. And for those of you who are looking carefully, you may have noticed that there's been no change here to X bar, even though it turns out that for this particular sample, which had the var value outside, its average value fell exactly on the average. So it actually didn't matter in this example. But the important point is that we have here a new R bar that we're using, and we have new upper and lower control limits that we are going to use for checking if our process is in control. And finally, we now see when we use our new upper and lower control limits for the range and the X bar, that our sample values are all within the control limits. Our process, we can say, is in control. And we expect, of course, that 99.7% of the net weights of chemical in the filled bag will fall within these limits. And if it doesn't, we will look for an assignable cause and try to eliminate that assignable cause. And here we have then a real picture of SPC. This is the X bar chart and the range chart from a semiconductor in production plant. This is from a thickness measurement, and here you can see it means X bar and R, and SPC chart you can see up there. So this would be something that then you could see in the factory, that the operators could see to see how the process is running. All right. So I hope you followed that. I just want to highlight a few important points about X bar and R charts. They have many uses, for example, to control a process at a given target or nominal value, and to maintain a process at a current level. And of course, as a troubleshooting tool, if something has happened, you can go back and look at these charts and try and find out how your process is affected or what caused the problem. And also as an acceptance tool, and what this means is if you have a new machine that you'd like to bring online, you can then process samples through this machine process product through that machine, then you can take samples and you can see how the X bar and R values behave for that machine. Now, one of the most important things, of course, is to we talk about this a little bit later, is to select which variable you're going to look at, which process parameter, process characteristic you want to monitor. And you can't monitor everything. It only makes sense to find the most important variables. And this we do as part of the SPC implementation. And has happened to me very often. Sometimes there'd be an indication of a problem from a control chart, and it was simply due to an error in the measurement. Or when you have a new product, it could be even an error in the test structure. So preparing the instruments is very important. Instruments and test structure. If you have poor instruments, they can indicate a false alarm, or they can also give you rubbish values and contribute to poor quality of the end product because you're not producing what you expect. I want to talk very briefly about rational subgrouping. Subgrouping here means sample. This means the decision on how to perform the sampling to get the most out of your control chart data. And we were looking at processes where we had samples taken as a function of time, which of course is the most common. Maybe your process will deteriorate over time, so we would take samples over time at regular intervals. And then as the process changes, we would then see what we would then discover the problem using our control charts. But if we had, for example, a process where we had different operators and they would make a difference in the quality of the process, maybe we should take samples based on the different operator. So this type of subgrouping is then called rational subgrouping, and we have an additional case study lecture on this topic in the course. And finally, we need to talk a little bit about control and capability, and please put a star by this in your lecture notes. So we talked about process capability in session 6. Now, process in control does not mean that a process is capable. It means that the process is consistent. Capability means that the process is producing products within customer specifications, not this. It's within control limits, and this is within specification limits. These are two very different things. Capability means the process is producing within the customer specifications, and a process in control does not automatically mean that the process is capable. And if it's not capable, then a capability study is needed to verify if the process is in control and also in specification or capable. So another way of improving the sensitivity of the X bar chart is to use what we call warning limits. So if here's our center line, and we talked about the 3 sigma limit, the lower control limit, and the 3 sigma limit, the upper control limit. So we can also have a 1 sigma or 2 sigma limit, plus or minus, on either side of our center line. And what you can do are have rules that are put in place to help discover a sign of a cause is using the warning limits, using these 1 sigma or 2 sigma warning limits. And an example of such rule would be here. When you have 3 consecutive measurements and 2 of the values, none of them are outside the 3 sigma limit here, but 2 of them are outside the 2 sigma limit. This example here, again, we have the center line, we have the 3 sigma upper and lower control limits, the 2 sigma and the 1 sigma warning limits, our center line, and we have here a sequence of 5 measurements, and here not quite consecutive because we have 1 there, but out of these 5 measurements we see that 4 of them are below the 1 sigma line. So these types of rules can be used then to improve the sensitivity of your X bar and R charts. And these are referred to as the Western Electric rules because they were originally recommended in the handbook published by Western Electric Co. So you can see 2 of 3 consecutive plots fall out of a 2 sigma warning limit, 4 out of 5 fall outside of a 1 sigma warning limit on one side, and more than 7 consecutive plots fall above or below the center line, or there's a run up and run down, and that we show here. You see here that you have 6 plots, 6 sample measurements that are going down, and here you have 7 that are below the center line. So these are just to give you an idea of some of the other uses or other sensitivity uses of the control charts that you can put in place. So we just have one last slide, and this is to talk about statistical process control, or SPC. Now, at the very beginning, we talked about quality systems and quality management and how it had developed from simple quality control, which was just an outgoing inspection. And we today have very sophisticated use of statistical principles to control processes. And this statistical process control, or SPC, is at the heart of effective quality programs and quality systems. Now, if the first step, if you are in an organization that wants to implement or improve SPC, would be to form a quality team, a cross-functional quality team, which should include manufacturing, product design, quality, even maintenance, and certainly operators or engineers who are involved in the process, and of course, the customer relations. And this team then should identify the key processes and key variables that could be under SPC control. These need to be prioritized. You cannot cost-effectively monitor everything. So it could be because you have a key product or a critical step in the product, or you have key customers interested in a specific product. Could depend on the cost of implementation or the feasibility of the measurement, or even on how quickly you can implement the SPC. So once this variable has been then selected, you then have to decide what type of variable you have. And we did this last lecture. You can either have an attribute variable or a measurement variable. And in this lecture, we, of course, have been looking at the measurement variables. We've been looking at the X bar and R charts for, if you have a sample size between 2 and 10, you can use your X bar and R charts. So then you want to create your X bar and R charts and proceed as we just did. Take 25 samples, compute the control limits, repeat that until you have your process under control. Once you find and eliminate, of course, all the assignable causes. And there is a case study in this course to help you practice this. Once you find an assignable cause, of course, you realize that the variability has gone down, and you should go back and recalculate your control limits. And finally, when you get your process in control, then you can move on and do a capability study. So you've got to get your process in control first. No use looking at capability until you have a controlled process, and then you can look at the capability of your process. And here, you're looking here again at the specification limits. And you see, is your process capable? And then if it's not capable, you can use CP or CPK, for example, then you would need to put in some kind of customer change and go back, monitor your new process, generate, of course, new types of control charts with new types of control with improved control limits, and repeat the process again. So there is also a second case study for you to look at then, this aspect of the SPC.